Okay, so finally we are ready to talk about linear programs. A mathematical program, as we mentioned, in general may be expressed in this way, right? We have m constraints. They are inequality constraints. We are minimizing an objective function. Our decision variables may be expressed as a decision vector x. This particular mathematical program is a linear program, is an LP, if all these functions are linear functions. So linear functions in some cases require specific definitions, and we sometimes use definitions like there is a linear mapping, blah 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 blah. We will skip those rigorous parts. Basically, if a function is linear, it may be expressed in this way. All your decision variables, they are put into a function in an additive format. Okay? Each decision variable may have a coefficient in front of them. So there is a multiplication between a coefficient and a variable. But you don't see two variables multiplying each other. They don't divide each other. There is no x1 square or whatever thing. There's no square root. There's no sine, cosine, tangent, whatever. You only see additive terms. Okay. So if that's the case, then you have this particular linear function. It may be expressed according to your sigma notation. Okay, I hope everybody is familiar with this one. This simply means a1 x1 plus a2 x2 blah 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 to an xn. So when we have this, we say all these aj, again, they are real values. Okay, all these aj, they are coefficients of this particular linear function. Okay, and we may write a as a collection of a1 to an. A again is a column vector here. Then in that case, we may also express our f of x as a transpose x. A is a column vector, so once you transpose a column vector, it becomes a row vector. X is a column vector, and they all have n components, so they may be multiplied together, and you get the inner product, which is indeed exactly this a1 x1 blah 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 up to an xn. So a very quick example shown at the right is that you want to minimize x1 plus x2 subject to linear constraint 1, linear constraint 2, some sign constraints, and you may see that sign constraints by nature, by definition, is linear. So this is a very natural linear program. So in general, any linear program may be expressed in the following way. So we are trying to minimize a linear function. So we may write it as c1 x1 plus c2 x2 plus dot 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 plus cn xn. So in that case, we may use this summation notation, and cj are the objective coefficients. Okay, we call them objective coefficients because they are the coefficients in the objective function. We also may express each of these constraints in this particular way. So the left-hand side is always the sum of several terms, all right? a1, x1 plus a2, x2, etc. It's just that now we have several constraints. So the constraint coefficients, must be distinguished from constraints to constraints. So aij can be considered as the jth coefficient for constraint I, or the constraint coefficient for xj in your constraint I. Okay, so that's pretty much the meaning of aij. It's the coefficient of xj in constraint I. So lastly, your bi here is the right-hand side value for your constraint I. So this is a general way to express a linear program. We will use it from time to time. If you like vectors, then we know that this particular summation is nothing but a vector, where C is a column vector and C transpose X simply means this summation. And for each constraint here, you may also express it as AI transpose X. And your AI again is a column vector. which collects all the coefficients you need for this particular constraint. Okay, so lastly, if you don't just like vectors, you even like matrices, this particular set of constraints may be expressed in this way. Okay, in this case, your A is really a collection of A11, A12, A13, A14, and A21, A22, A23, A24, and so on. Suppose we only have these 8 numbers. That means we have 2 constraints and 4 variables. Okay, this is going to be multiplied with x1 up to x4, the column vector here. So A is this particular matrix. X is this particular vector. Once you do the multiplication, they should be less than or equal to B1 and B2. You have this part, right? This and this. The inner product gives you an inequality with respect to B1. And then this and this with respect to B2. So altogether, that's simply a matrix inequality. All right? And with that matrix inequality, you are done with expressing your linear program. So we will stop our general description about linear programs here. Pretty much what we are doing is that we are having several ways to express a general linear program. Either we write down all the numbers specifically, or we utilize vectors, or we utilize matrices. So when we are still beginners, maybe we are more familiar with the first way. But from time to time, we will gradually get used to the second way or even the matrix way. But hopefully, at least you understand they are all equivalent. It's just different ways to write down a single formulation.